Okay, so hello. Okay, so let's get started. So let's continue to talk about databases. So before we start, right, so let me just say thank you for all the feedbacks that you gave us during the teaching evaluation, right? So both the critical ones and also the positive ones, right? So some of them we will try our best to fix. Some of you guys say, okay, you want me to open open the camera to help you to concentrate. So here I am. I'm your database professor. Just to convince you I am, I'm wearing a shirt with a database on it. So, and there's some other feedback that's probably too late for to fix, right? For example, a lot of you guys talk about the Excel section, and definitely we should refine it and improve that next year, right? So like I read all of your comments. We'll definitely do a better job next year, right? So I just want to thank you, not on behalf of myself, but also on behalf of all the students who's going to take the course next year, right? So they are going to have a much better database course, not because of me, but because of all of you guys, all the feedback you gave us. Okay, great. Transactions, right? So last week we talked about transactions. So essentially, we start from this motivating example, and we talk about, yeah, I mean, if you allow me to mix all those instructions in a way that I do not control, right? So there could be a whole bunch of problems. So we want to introduce the notion of groups of transactions, right? So, and I can say, okay, so now I begin a transaction. Here's a whole bunch of instructions that I have, and also I end the transaction. Once you define this notion of a group, right? So you can actually enforce a whole bunch of properties that you want this group to have. And that is where we are. So what is a transaction? Let's just refresh our memory about the formal definition, right? So we abstract the database as a whole bunch of named data objects, right? So we don't care whether it's table, we don't care about the row, whether we don't care about it's a value, whatever, right? We don't care. Database right now is a whole bunch of data objects. Each one of them has a name, and each transaction is a sequence of read and write operations. For example, you can read the variable A into memory, right? You can manipulate it, or you can write it back, right? So this is the kind of two critical operations that we are allowing in a transaction. And when we think about transaction, we care about the IO pattern of the transaction. And that is because we think about transaction as sequence of those read and write operations. So a new transaction starts with a special keyword called begin, right? And can end in two ways. You can either commit a transaction, right? If you do that, the database will make sure all the changes that this transaction is doing to your database is going to be reflected on hard drive. And even though you pull the plug out of your database and you reopen it, all the changes will still be there. Another way to end the transaction is abort, right? So in this case, all the changes that have been done by the database is going to be undone, right? So and it is as if this transaction never happened, right? So multiple people multiple players in the system can trigger abort, right? For example, sometimes the user can trigger abort. User say, okay, so I have done a whole bunch of things. I don't want to do it anymore, right? So let me abort this transaction. It's fine. It could be triggered by the user, but it could be also triggered, for example, by the nature, right? So for example, someone pulled the plug, or the whole system is down, right? And then essentially all the transactions are aborted, right? Automatically, right? So always can be triggered by the systems, right? When the system, for example, have deadlocks that we talked about last week, it need to kind of abort some transactions to break the deadlock, right? So in that case, the system could actually abort a transaction. Okay, so whenever transaction get committed, often like dominating the case, it is the user who is initiating that. But when the transaction is aborted, right, there are multiple players that could do that. And we talk about essentially 4 different properties that we want to enforce by having the abstraction of a transaction. Right? We talk about atomicity, consistency, isolation, and durability. So we spent 2 lectures essentially talk about isolation, right? So how can we make sure when you have multiple transactions in the system, it is as if all of them are executed in a sequential order, right? So that also have a very strong connection with consistency, right? Because if every single transaction is going to bring your database from a consistent state to another consistent state, when you have isolation, right, the parallel execution of all those consistent transactions will also be consistent by itself. And we talk about two different ways, right? We talk about how to build a scheduler, right? So there's optimistic view that you can take. There's a pessimistic view that you can take, right? Depending on like which view you take on your workload, you end up have very different systems, right? So if you take a very pessimistic view, you probably will use locking to enforce isolation, right? If you take an optimistic view, right? We talk about optimistic concurrency control on Friday, right? So you can do concurrency control using timestamps, or can do snapshot isolation. So today, let's switch gear and talk about essentially the two other properties that we want to enforce by using the abstraction of a transaction. And that is atomicity and durability. So let's refresh our memory about this, right? Because when we talk about this like 2 weeks ago, right? What is durability, right? So durability means that if the system crashes after a transaction commits, we need to make sure that all effects of the transaction remains in the database. So as a kind of a practical example, right? So when you go to the bank and you deposit your money, right? So once the bank tells you, okay, your money is here, right? So just like you commit your transaction, after that point, you will not worry about the bank come to you to say, okay, so my data center is down yesterday, your transaction get aborted, the money is not here anymore, right? So you want to make sure as long as the system tell you, okay, it's committed, it's done, okay? Nothing will change that state. That's what we want to make sure. So essentially, if you have a transaction look like this, right? You have SQL1, SQL2, two different instructions. Durability means that if the system crash at this point, after commit, right? You want to make sure when you reopen up the database, all the changes that is done by this whole transaction will still be there. Atomicity is very similar, but look at the whole problem from a different perspective. Okay, so essential atomicity means that each transaction is all or nothing. Okay, you never have a transaction that is halfway done. Okay, so essentially, when you have a transaction running the system, and no matter when the system crashes, we'll reopen it, you always have only two possible states. Either all the changes from the transaction are reflected in the database, or none of the changes are in the database. You will never have a case where half of the changes from the transaction are in, but the other half is not there. That is not something we want. So to compare that with durability, right? So essentially we care about system failure at different point of the life cycle of the transaction. For durability, essentially you say, okay, after you commit, I give you a guarantee that all the changes will be there. Atomicity means that assuming the system crashes in the middle, okay? So after you run SQL1, you haven't run SQL2 yet, the system crash. Atomicity means that if you recover the system from this failure, right? So you can only have one state where SQL1's effect will not be there. Meaning that when you recover the database from the failure, right? You will have a database as if this transaction never happened. And assume the system kind of magically, right? So crashes here, right? So maybe right before the commit, but after SQL2, right? Atomicity means that if you recover the data from the failure, you can be in two different states, right? Both are fine, right? Either none of the change, like none of the changes done by SQL1 and SQL2 are in database. And second is all the changes by SQL1 and SQL2 are in database. Okay, both are fine. But whenever you recover your data from failure, you will never have a transaction that's halfway done. Okay, that's atomicity. A transaction is a group. The execution need to be atomic. Okay, so this is the two properties that we are going to talk about today. Okay, before we talk about kind of the mechanism that we are going to use to recover from failure to enforce durability and atomicity, right? Let's look a little bit in detail about our assumption on what we are trying to recover from, right? Because there are so many different types of failures. We need to kind of scope ourselves, right? So we want to recover from essentially abort of single transaction, right? So here, essentially, when you like talk about recovery, right? I need to be able to undo a single transaction when the user asks me to abort it, right? So here, the user is kind of the failure, error code failure, right? So user say, oh, like abort this transaction, I should have some way to undo it, right? So, oh, there are system crashes, right? So you could lose your main memory, someone put a plug, but your hard drive is still fine, right? So in this case, when I do the recover of my database, I need to redo all the committed transactions, right? On the other hand, I need to undo all the transactions that was active when the system crashes, right? So all of the transactions will not be done, right? So the system need to abort them, right? So I need to undo all of them, right? When there's system failure, I need to redo all the committed transactions whose changes haven't been reflected to the hard drive, and I need to undo all the active transactions at the time of failure. So there could be other type of failures. For example, I could have system crash that I lose the whole thing, right? I lose my main memory. I also lose my hard drive. Some of the hard drive failed, right? So in this case, when I'm doing recovery, right? So we are talking about I need to read a backup of my data from the tape or from some replica of my data, right? So there are different type of system failures, right? And then there are different type of ways that you can recover from them. So in this course, right? So we are going to look at undo and redo, okay? So we are going to say, okay, we want to make sure if you abort the transaction, I know how to undo all the changes. Okay, so typically by just restoring the database to the before image of the value. And then I want to make sure I know how to redo the changes of a committed transaction if they haven't been reflected on my hard drive, right? So typically I do that by restoring the after image of all the values. Okay, so I will always assume my hard drive is fine. Okay, I could lose information in my main memory, but my hard drive is still there. Okay, so that is the assumption that we are going to take in this course. So once you assume that, I I have my hard drive, right? So you are actually way more powerful than, for example, than the cases that you have system failure, but you lose the whole hard drive, right? So the high level idea there is because your hard drive is there, we actually try to log all the transactions and keep the before and after images of their changes to allow me to undo and redo them if I have to do it. So that's a high level idea, right? But when it goes to reality, when you really cares about the last bit of performance, right? There are a lot of considerations that you need to do to really make sure the whole thing is both correct and efficient. Okay, in this lecture, we are going to look at the problem in three different aspects. We are going to first talk about the theory, okay? So we are going to talk a little bit about recovery theory, and then we are going to introduce a very natural, but as you will see, it's a non-trivial way of writing down the before and after image, and that is by using something called the read-ahead log. And then we are going to look at a little bit more complex case. That is, we are going to think about how to enforce durability and atomicity when you have multiple databases in a like working in a federated or in a distributed way. Okay, theory first. So before we talk about theory, let's define one concept. So if you have a schedule, remember what is schedule, right? So you have multiple transactions and you mix their instruction, right? One schedule is simply one way for you to mix all those instructions. We talk about that a lot when we are talking about isolation, right? So here is the same concept. So given a schedule is two transactions or multiple transactions, there's T1 and T2, okay? So we say T1 read from T2. If T1 read a value written by T2 at the time when T2 was not aborted. Okay, so essentially that is somehow similar to the notion of dirty read, right? So that is you have T2 like right now has not been committed, right? So and then T1 actually read the value written by T2. Okay, so we are going to see some example to make this more concrete, right? But when this happens, we say T1 read from T2. Okay, so this is the thing that we are going to use again and again today. So what is the game we are trying to play here? Okay, so in terms of our theoretical understanding of recoverability, right? So we try to classify all those schedules into different family of schedules. So as you'll see, we are going to talk about 3 different families: RC, ACA, and strict. Okay, so very similar how we deal with schedules when we talk about isolation, right? So there's all the possible schedules. There's a serial schedules. There's the schedule that's conflict serializable. There's the serializable schedules, right? You have different families. Each of them have different properties. So here we try to do the same exercise, but for recoverability. Right? We try to understand how can we define different family of schedules, and each family have different recoverability properties. Okay, we are going to look at this, and then we are going to say, okay, our goal is to make sure all the schedules is in this family. Okay, and then we are going to introduce how we can do it, right? But let's try to understand that from a little bit more abstract theoretical aspect. So the first family of schedule, right? So let's go through the definition, and then we are going to go through examples. The first type of schedule is something called recoverable schedule, right? We say RC, okay? So essentially, a schedule is in RC, is recoverable if the following is true. That is, in that schedule, if Ti read from Tj, remember what do I mean by Ti read from Tj? It means that Tj update the value on something, and then before Tj aborted, Ti read that value. Okay, so if Ti read from Tj and commit, then we have the commit time of J is smaller or earlier than the commit time of I. Okay, if this is true in that schedule, we say that schedule is recoverable. Okay, so this is the first family of schedules that we define. So the second family is something called avoid cascading abort, called ACA. So we are going to go to definition, right? And we are going to look at them in detail by examples. So here, essentially, if your schedule is in ACA, it means that in that schedule, if you have 2 transactions, Ti and Tj, Ti read X from Tj, we want to make sure Tj commit before Ti reads that. Okay, if that is true, in that schedule, with that schedule is in ACA. So the third family is called strict schedule, right? So which actually extend ACA, but also consider writes. Okay, not only read. Essentially, if Ti read from or overwrite a value written by Tj, then you want to make sure only 2 of these things could happen. Either Tj commit before the read and write from Ti, or Tj abort before the read and write of Ti. If this is true, then we say the schedule is strict. So this is all very abstract. But then let's look at some examples to understand what are we really trying to capture by these 3 family of schedules. So let's look at the recoverable schedule, right? So here's the definition, right? If Ti read from Tj and commit, we want to make sure Tj commit before Ti. So the high-level intuition is, if a schedule has this property, you will never be in a situation that you need to undo a committed transaction. You have the hope to enforce durability, okay? Otherwise, if I have to undo a committed transaction, there's no way I can give you durability. And that is when I say the whole thing is actually not really recoverable, right? Because there's one property I cannot really guarantee. So let's look at this example, right? Then the whole thing will become really clear what we are trying to capture. Here you have two transactions, T1 and T2, right? T2 first write X, and then T1 read X. And because when T1 read from T2, T2 hasn't been aborted yet, right? So essentially, T1 read from T2. Okay, so that's what this kind of two kind of red rectangle and this kind of red line try to capture. Okay. On the other hand, when Ti read from T2, I also have the commit time of T2 is earlier compared with the commit time of T1. Okay, so you can see this two parallel type of structure. Okay, so T1's read happens after T2's read. Oh, but on the other hand, T1's commit also happened after T2's commit. Okay, so if all of the read from relationship have this type of parallel structure, right, then this schedule is actually recoverable. So to best understand what it's trying to capture, let's look at the other way around, right? What if I do not have this? What if I have T1 read from T2? However, T2 commit after T1 commit. Okay, if you have one of these cases, then this schedule will not be in the recoverable family, right? So what would happen, right, in this case? What would happen is, assuming your system just crashes down before T2 commit, what do you need to do? In this case, because T1 already committed, right? But T2, you want me to abort T2? But if you want to abort T2, right, I need to undo the write X in T2. I need to bring the database to a state before T2 write to the database. However, my T1 already read from that. My T1 is aware of the value that T2 want to write. And then I base my calculation on that, and then I commit. If you want to undo T2, you also need to undo T1. But T1 already committed, so I cannot undo it. So that is a case that we want to avoid by making sure all the schedules that we want to schedule in the database should at least be recoverable. Okay, so that's why we define recoverable schedule in this way, is really try to avoid cases like this. Okay, so is there any questions about what we are trying to do and about definition, about this example? If you have any question, just speak up. Okay, so now let's move forward. The second family of schedule is called ACA. Okay, so it's going to be a little bit stronger than recoverable, right? Because yeah, recoverable is great, right? Now we have the hope to enforce durability, right? But on the other hand, yeah, there could be other problems that we will see. What is the definition of ACA? Essentially, a schedule is in ACA if the following is true. That is, if you have Ti and Tj, that Ti read X from Tj, we want to make sure Tj commit before Ti read it. Okay, the high-level idea is to make sure that if you abort a transaction, for example, if you abort Tj, it doesn't cause cascading abort of other transactions. So let's see why that could be a problem if a schedule is not in ACA. Okay, so this is one example of a transaction that's in ACA, right? So here I have T1 read from T2, okay? And then I also have T2 commit before this read, okay? If you always have this type of structure, right, then this schedule will be in ACA, okay? So now let's look at one schedule that's not in ACA to see what could be the potential problem here. Yeah, so what if the other way around? You have T1 read from T2, and then you have T2 commit after T1 read. Okay, so that's the precise thing that violates our condition, right? In this case, what could happen? So let's imagine the system crashes here. right before T2 commit, right? So in this case, I need to abort T2 because, yeah, for some reason I need to abort T2. What should I do with T1? In this case, I also need to abort T1, right? Because T1 have already done a whole bunch of calculation based on the value written by T2. If you want to undo T2, you also need to undo T1. Here, you can already see some progress, right? Because T1 hasn't committed, right? In principle, I could abort it, right? So, I mean, it's not ideal, but in principle, if you want, you could abort T1, right? It won't hurt durability because T1 hasn't committed yet. So, but the problem is, yeah, so this is something that we also want to avoid, right? We want to have this kind of isolation is a little bit wrong word to use, but we want to make sure all those transactions are relatively more independent. That is, when someone screw up in their transaction, I want to abort. I don't want that mistake to propagate to my transaction, right? Why and why would you abort my transaction because some other people want to abort their transaction, right? So that is the thing that we want to avoid, right? And that's something called cascading abort. And if your schedule is in ACA, right, you can kind of like avoid that. And the third family of schedules is called strict schedule, right? So here's the definition, right? It's pretty much ACA, right? But it kind of extend that to write. So essentially, a schedule is in strict schedule if, assuming you have TI, either read from TJ or overwrite a value written by TJ. We want to make sure either TJ commit before the read and write, or TJ abort before the read and write. Okay, so and this is actually like another thing that is they try to enforce that when I try to undo a transaction, right? I don't need to undo the change of another transaction, right? I care about the read, but I kind of also care about, for example, what if that transaction like writes something? I also need to undo it. I also don't want that to happen, right? Very similar to ACA, but extend that to both read and write, right? So this is just one example, right? So for this schedule, it's strict. Why? Because T1 overwrite T2, okay? But T2 also commit before this write, right? This is fun. So what if you have something like this? You have the other way around, right? If T1 overwrite T2 and T2 commit after T1, right? So here, right, so we do the same kind of thought experiment, right? What if you kind of system crashes, whatever reason, you want to abort T2 before the commit? Okay, so here, right, I also need to essentially undo the write operation in T1 when I bring back, like when I try to kind of undo all the changes from T2, right? So, and if you have something in strict, right, so that is not something that you need to worry about. Okay, so if you put them together, right, so we have this. So we have in the center the serial schedules, right? So that is schedule transactions one by one, right? So it's already recoverable because, I mean, you are doing them one by one, right? So, and then you have the strict schedule, right? Contains a little bit more than serial, right? And then you have ACA, you have recoverable, and you have all the possible schedules. And if you think about this together with serializability, right? So serializability is a different dimension, right? So at the core, you have a serial schedule, right? And then you have kind of a larger family, which is conflict serializable, right? That's something that we talked about last week. When you are building a database system, and at least you are building a traditional kind of relational database system on hard drives, right? The game that we want to play is we only want our database to allow schedule in this green region. Okay, we want to make sure we only allow schedule that's strict. On the other hand, is conflict serializable. Okay, so someone raise hand. Go ahead.
Yeah, could you maybe re-explain the strict?
Yeah,
I didn't quite catch that, especially the example. So T2 aborts. Why would T1 also need to be undone, right? Because if T2, for example, writes 1 and then T1 writes 2, and now T2 doesn't commit. But I mean, T1 commits if T1 commits, since the write is after the write of T2, like the value, like whatever T2 has written, that doesn't matter. Do you see what I mean? So if like T2 get like
yeah. So I see what you mean, but I want to bring the database to a state as if I want to bring the database to a state that before T2. Right. So for example, the original value is 0, right? And then T2 write 1, T1. Oh, sorry, it's a very confusing way to say it. So the original state is 0, T2 write 2, T1 write 1. Okay. And then T2 abort. I need to bring the database back to 0.
Ah, okay. I see.
So I also need to overwrite what the T1 has.
Yeah. Okay, that makes sense. Thanks.
Right. Makes sense. Okay. Cool. So any other questions? Okay, great. Yeah. So just remember this kind of, we have essentially 2 hierarchical structure over all the possible schedules, right? So you have one hierarchical structure based on recoverability, and you have another hierarchical structure based on serializability. Okay. So when you try to build the kind of the traditional database system, the most standard way, right? We want to make sure you get their intersection. We want the schedule to be both strict and also conflict serializable. Okay. So how can we do that? Right. So last week when we talked about locking, like two-phase locking, we know how to enforce conflict serializability, right? How can we also enforce essentially recoverability, right? To make sure the whole thing is strict. It's actually interesting because remember we have one schedule called strict two-phase locking, right? So if you wonder why we call that strict, but don't use some other word for that, it's because the following claim is actually true. That is, if you do strict two-phase locking, it's going to ensure that the schedule is going to be both serializable, also conflict serializable because that's stronger, right? And also strict. Okay, if you do strict two-phase locking, that's what's going to happen. Let's refresh our memory about what strict two-phase locking is, right? So it actually try to provide the schedule about when should the transaction acquire locks and when should the transaction release locks, right? So it's kind of partition the transaction in 2 different phases. So there's a growing phase, so in which the transaction can only request locks from the lock manager, and also it's going to keep all the lock until the end of the transaction. Either commit or abort, doesn't matter. It's going to keep the lock until the end of the transaction. Okay. If you lock it in this way, then you are using strict two-phase locking, and this is going to enforce all the schedules to be both conflict serializable and also strict. So how can we prove that? We are not going to go through the proof, but the high-level idea is kind of simple, right? So for example, you have T1 and T2, okay? And T1 access something, I mean, essentially T1 want to read from T2 or try to overwrite T2, okay? So in that case, because T2 is holding the lock until the very end, the access from T2 must happen after T2 release the lock, right? And because in strict two-phase locking, T2 only release lock at the point of commit or abort, the access of T1 will always happen after the commit or abort of T2. That is almost the same thing as the definition of the strict schedule, right? So like remember like our definition, right? So we want to make sure whenever Ti read from or overwrite the value from Tj, right? So Tj need to commit or abort before the read and write could happen, right? So and you can see why when you are using strict two-phase locking by holding all the lock toward the end of the transaction, that actually enforce precisely that condition. Okay, so this is really high-level idea if you really want to prove it in a very precise way. So this is just kind of one example, right? So assuming T1, right, want to read from T2, right? So And of course, right, so I need to wait until T2 release the lock, and T2 will not release the lock until the end of the transaction, right? So this type of structure is kind of enforced by this type of lock-in strategy. Okay, so recoverability is something that if you look at traditional database theory, look at those papers, or talk to people about transactions, right? Isolation is always the first thing come to everyone's mind, right? So I want to make sure there's parallel execution is correct, right? So, but recoverability is at least like equally important, right? Because it actually ensures the state of the database correct when there are failures. And we are building a real world database systems, right? Serving millions of users for a couple of years, right? Failure will be there, right? No matter how good your infrastructure is, it's going to fail at some point, right? Recoverability is very important because it ensures the state in the database is consistent or correct. Okay, so whenever you have problems related to recoverability, and often it's very rare, right? Because yeah, failure is something that we don't want to think about and hopefully very rare. But whenever you have problems, you are not being careful. Problems related to recoverability are often very, very expensive and sometimes kind of impossible to fix, right? For example, if you ever allow a schedule that's not in RC recoverable, right? So it means that, okay, you run a program, you get some data, right? You finish the program, right? You write a report, you submit the paper, you talk to your boss, whatever. And then database come to you, okay, what you read actually is, yeah, I mean, you should undo all those things, right? I decide to abort your transaction, right? That could be very expensive, right? And also it's not really clear in general how to solve that, right? So if you allow kind of a schedule that's not in ACA, right, in your system, right, it actually means that, right, like whenever someone else screw up their transaction, potentially my transaction could also be aborted, right? Why, right? So you have those kind of less isolated environment between different users, between different transactions, right? And sometimes when there's strong dependency between all the transactions, oh, you are going to have thrashing behavior. That is, all the transactions keep aborting each other, right? So if you are not being careful, right? If you allow some schedule that's not strict, right? So as we will see, the like recovery after failure become very complex, right? Because you need to think about whether I should like overwrite a committed transaction, right? It's not really clear what that even means, right? So, okay, this is about theory, right? So given a schedule, we define 3 different family of schedules. Each one of them have different properties about recoverability. And I think we get on the same page that we want to make sure we only allow strict schedule. And we see how to do that using strict two-phase locking. And now let's try to switch gear and try to understand a different question. Assuming my system only allow strict schedule at this moment, assuming I'm using strict two-phase locking, and now my system failed, what should I do? How can I recover my database from failure? So that goes to the second component that we are going to talk about today. And that is how to do database recovery using logs, okay? So before we go to this section, right? So any question about theory? You have any question, just speak up. Okay, cool. Logs. Again, let's talk about assumptions and intuitions. And then we go to the technicality about this. So what is our assumption? When we talk about this, right, in this course, we assume your secondary storage is safe. That is, you will never be in a situation that you lose your hard drive. Okay, you can pull the plug of the machine, and that's pretty much like the kind of our target, right? Someone put the plug of the machine, you restart it. What should you do, right? You assume your disk is safe. And one thing that's different from when we talk about isolation is in transaction, whenever I read something, we assume it does not reflect on disk immediately. It only gets reflected if I explicitly ask you to flash it. Okay, so I have something called output A. So I actually introduce another kind of instruction, right, called output A, right? So from now on, when we talk about transactions, right, when I write something, it does not get reflected on disk. It gets reflected only when I output it explicitly, okay, flash it out, okay? So essentially, I mean, we start to look into more details about the interaction between the memory buffer and hard drive. Okay, when we talk about isolation, we don't have to do it, right? So now when we talk recoverability, we need to open it up a little bit, okay? From now on, when I write something, it's in memory. When I output something, you bring that in-memory variable and put that on disk, okay? So that's our assumption. That's different from last week. The high-level idea is by using log, right? So essentially, what is a log? A log is a file that you open for appending only. That is, I can only append things in the log. I can add in tuple, that's it. I cannot delete anything from the log. I cannot do random access in logs. I can only append, okay? So it's stored in your database as if it's another file, right? So, and first you store it in memory buffer. You actually have part of the log in your in memory. And then periodically you flash the log to disk, okay? So as you can see, right, as you can imagine, what is the fundamental question here? The fundamental question is, when should we flash the log from memory to my hard drive? And that's something we are going to look at. Depending on what you are storing in your log file, right, you have different strategies about when should you flash it to hard drive. So what should we put in a log file? Yeah, we are going to put a whole bunch of record, right? So again, we can only append it, right? So we can say, yeah, there's one record we can say is, okay, I started transaction T. That's something that I can put in the log as one record. I can commit T, I can abort T, right? You have 3 different records. You can keep appending to the log, right? I could have in my log the old value or the new value of object X, right? For example, if one transaction say, okay, set X to 10, right? So you can put in your log to say, okay, the transaction T want to update the value of X to 10. Okay, you can just write that down as one record and append to your log. And then there's one operation that I can do on my log file, other than appending the records, is I can say, okay, flash the log, which means that I'm going to bring all those in-memory part of the log and read them back to my hard drive. Cool. This is pretty much the only 2 things I can do to my log file. I can keep appending stuff. I can flash it out. Okay. So also just want to like kind of get on the same page, right? So these are just logs, right? Whenever I write something, whenever I write in my log file that, okay, transaction T update X to 10, right? It doesn't mean that X is actually being updated on my hard drive, right? Because they are just log record. It means nothing, okay? So when I actually write commit T, it doesn't mean T is committed. I mean, simply one record, okay? So down the road, we are going to look at how to associate these records to the real meaning, okay? But do not take that for granted in the sense that just because there's a commit T in your log file doesn't necessarily mean, well, I mean, and just because there's a commit T in the in-memory part of your log file, right, doesn't mean the transaction is committed. Okay, so there's a difference between what actually happened and also what is in the log, what is in the in-memory part of the log, and what is in the kind of on-disk version of the log. Okay, so there's kind of very delicate relationship between all of this. So just do not take that for granted to say, there's a commit T, it might be committed. I mean, it doesn't work that way. Okay, cool. So this is about logs, about assumptions, right? So I think we have 1 minute earlier. Okay, so let's take a break. when we get from the break, we are going to talk about how to use all those logs to enforce recoverability. Okay, yeah. So in the meantime, you have any question, just speak up. Yeah.
Okay. Just a quick question. Can you go
Yeah.
back to the slide one before?
Yeah.
Yeah, it says write does not reflect on disk. Is that so is it saying that why does it not reflect on disk? I would imagine maybe I didn't pay attention, but
Oh yeah, write only changes the buffer.
I mean,
yeah.
So what do you mean? It only changes the of oh. And so what is output then? So what would that be?
Yeah, so like output going to kind of flush the buffer.
I mean, it's kind of like, so how do these correspond to then SQL statements, right? So if I say write, then it would go to, you would say it's to buffer. So when exactly is this output going to?
Yeah. So I mean, and this is a very good question, right? So like when you are doing the real database, right? So you write a SQL query. So the database is going to actually decompose them into a whole bunch of write operation to the buffer, right? And then the log, and then the recoverability, the scheduling part will periodically flush them out to your hard drive.
Okay.
But it need to do that in a way in coordination with the log. So as we will see.
Okay.
Yeah. So like it cannot. So the only reason we now kind of decompose this tool, right? So remember in isolation, right? So we don't decompose this tool. We say whenever you write, it's always on disk, right? So the only reason we kind of decompose this tool, right, is that the output of A need to have a very interesting correlation with the flush of the log, right? So like
also,
whenever
output and flush are not the same thing.
Output A is on the real relation.
Okay.
Flush a log is on the log. So log is a separate file.
Okay, but so what is output?
So output simply means like a flush. So output is essentially here means that I have object A. You change it in the buffer. I want to reflect that change to the hard drive.
Also, for example, when we're switching out a page, or like when we're done writing to one thing and then we want to switch something else into the buffer, is that like when we use output, or like when, or is it just something that database management system decides when it wants to do that?
Some of the output will be enforced by the system. For example, your buffer is full, right? So you want to evict some pages.
Yeah.
Essentially, you actually force system to output, right?
Yeah.
But sometimes the database will say, okay, now flush this out, because you said you want to commit. I want to make sure all of the changes are on the hard drive.
Okay.
So I will trigger output, right, from the system side. So it's going to get clear, like down the road, that when we look at the example, that you have the output A, right, and then you have the flash of the log. Yeah,
that makes sense. Thanks.
Cool. Okay, so let's continue. We talk about logs and we talk about our assumption on transactions, right? So let's try to look at one very simple strategy of doing logging and how we could use it to recover from failure, right? And then we are going to look at a very concrete example. You are going to understand what do you mean by write, what do you mean by output, right? By flash log, right? So we are going to go through that, okay? Using this example. So this strategy is called undo login. It's based on a very simple idea. That is, if one transaction modifies a database element X, we are going to write essentially one log record into the log, saying that the transaction T updated X, the object X. Here is the old value. Okay, so and then I'm going to flash this to disk before the transaction T changes X on disk. Okay, and then if the transaction commits, we will have a commit record in the log, and we want to make sure the commit record must be written to disk only after all other changes are written to disk. Okay, so we want to make sure we cannot write the commit record in the log file before all the changes of the transaction is done. Okay, so the hello idea is once you have this, if you have a transaction that has not been committed and you want to undo it, right? You can follow the old value in the log record to undo all the changes by revert all the values of X back to the old value. So now let's look at this, right? So the picture gets a little bit complex, right? But we are going to look at it. So on the left-hand side, you have your transactions, okay? So let's check this. You have your transactions. And then on the right-hand side, you have essentially two different things. You have the buffer, right? So in memory, you have one copy of the data object A and B. On your hard drive on disk, you also have your copy of A and B. Okay, so and we also have the log file in memory. So I didn't draw the log file on disk. Okay, but the log file right now, everything is, so this is the in-memory part of the log. Okay, so whenever I read something, so let's follow this line by line. Okay, so in the transaction, the first thing I do is, okay, I read A. So what is the effect that to my system? Okay, so I'm going to bring the value from my hard drive to memory, right? So as you can see, I actually bring this value to my in-memory, right? So now the in-memory copy of A will have value equals 8. I do this, right? And then actually increase. And then I kind of increase like this T, right? To 16, right? And then I write A. Okay. So here when I write, it doesn't get reflected on my hard drive. I only change my in-memory version of this. Okay. So as you can see, once I do this right, my in-memory version of A will change. Now it's 16, right? But my hard drive is fine. I mean, I'm still 8. Okay. And then when I read B, right? So the same thing happened, right? And I multiply by 2, right? And then I write B, I have 16. Okay. So at this point, the in-memory version of my database reflect all the changes I want to do from this transaction. But I haven't touched my hard drive yet. Okay, my hard drive is as if this transaction never happened. And if you look at my log record, right? So at the beginning of the transaction, I append essentially one record, right? Start T, transaction T started. Once you write it, right? So once you kind of write it, I kind of put one record into my log, say, okay, so transaction T want to change A. Here is the old value. I don't care what's the new value. I put the old value. Old value is 8. Okay, so new value is 16 in memory. I put in my log. Okay, old value is 8. And then once you write B, I put in my log a new record saying that, okay, transaction T want to update B. The old value is 8. And then before the transaction is allowed to make any changes on my hard drive, I need to make sure the log is on hard drive. Okay, so I'm going to flash my log in the sense that all of these 3 records is going to be updated on my hard drive. Okay, even if you pull the plug, right, you reopen it, you will see these 3 records on my hard drive after you flash your log. Okay, and then once you flash your log, all the kind of all the things in the log are already on hard drive. Now this transaction is allowed to make changes. Okay, so it's going to reflect the change of A, output A, right? So going to bring A, the value in memory to the hard drive. Okay, so as you can see, look at the state once you run output A. So the on disk version of A is going to become 16, right? It gets updated, right? And then it's output B. Once all of these are done, once all the changes from transaction is done, right? So this is the second condition, right? So once all the changes are done, you put a commit record to the log, and then you flash the log again. Okay, when you flash the log, this record will actually be on hard drive. Before you flash the log, this record is just in main memory. Okay, when you put the plug, open again, that commit record is not there if you haven't flashed the log yet. Okay, so this is a very simple example about undo logging. So it will become clear why we do a whole bunch, why we have all those 2 conditions. Once you think about what if the system fail at different points. Okay, so whenever, so think about that. Okay, you are doing undo login, and then the system crashes at some point, and then you reopen your database. You look at the log. So there are some transactions already have a commit record in the file, in the log file. What does that even mean? It means that all of those it means that that transaction is already after the flash log stage, which means that, right, all the changes of that transaction is already being reflected on your hard drive. Because we have the second condition, right? If a transaction commit, the commit record must be written to disk only after all other changes are done, are written to disk, right? Once you see the commit record in your log file, that transaction is done. Okay, you don't need to worry about it. It's not the transaction halfway done. All the changes are there. Okay, so essentially, when you recover, whenever you have a commit record in your log file, it means that it is a committed transaction. You do nothing. If you see there's a transaction without the commit record, it means that it actually means that maybe all the changes are already there, but maybe not, right? So we call those uncommitted transactions. Okay, so they do not have a commit record in the log file. So here, then what should you do? You start to try to try to find in the log file the start record of T. Okay, you try to find those with a start record but with no commit record. If there's only one such transaction, okay, you just undo with log, right? You scan the log from the tail to the head, right? And then whenever you see a kind of an old value, right? So you just replace your database with the old value, right? So, and then you write about T at the end of the log, you flash log, you are done, right? Essentially, when you recover, right? So here's a transaction potentially is halfway done. What should I do? I want to abort it. How can I abort it? And to bring the database to a state that as if this transaction never happened. How can I do that? I just use the old value that you put in the log to undo all the changes you have. If there's a multiple of those uncommitted transactions, right? Multiple transactions we start but no commit in the log, right? So again, you start from the end, right? But you kind of skip those updates made by the committed transactions, right? You write about T at the end of the log, you flash, right? For each of these uncommitted transactions, and you are done. So now let's look at one example, right? Because this could become a little bit abstract. So let's assume, still that like the transaction like in the previous example, let's assume the system crash at this point. It's very unfortunate, right? So you just put a start record in the log in memory, you haven't flashed it, right? You just read value of A from disk to memory, and then the system is done. And then you reopen the database. What would you see in your log file? In this case, everything in main memory is gone, right? You haven't flashed log yet. So your log in this case is actually empty, right? You see nothing, right? You don't even have the start T record in the log file. You don't even know that T exists, right? When we open the system. In this case, how would you recover? I mean, you do nothing, right? So like the T hasn't done anything yet, because there's no way that T have done any changes before, there's no way that transaction T has done any changes to your database, because before it is allowed to do it, you must flash the log. Remember, that's our first condition, right? So you need to flash a log before this transaction is allowed to do any changes on your hard drive. Because I don't see anything about this transaction, it means that even if you have that transaction, you haven't flashed your log yet. So you haven't done any changes to my database. When I recover, I do nothing, okay? And what if the system crashes here? It's the same, right? You haven't flashed a log. I mean, when you reopen the system, you have an empty log file. What if you crash here? It's the same. There's nothing there, right? All the write are actually in memory, not on hard drive. When I reopen the database, everything in memory is gone, but my hard drive there's no changes, right? And what if you crashes here? That becomes a little bit interesting. This is after a point that I already flashed my log. And then in the middle of this transaction, making changes to my hard drive, the system crash. When I reopen it, first one, what do I see in my log? In my log file on disk, I see 3 records, right? Because I already flashed the log. I see the start T, I see the old value of A, I see the old value of B. From that log file, what can I learn? Well, I know multiple things. First one, before I crash, there is a transaction T in my system. There's no commit, right? And it's maybe have already done some changes to my hard drive, maybe not, I don't know. Yeah, I don't know when did you kind of crash, and maybe you already updated some variables, maybe you updated nothing, maybe you updated all of variable, I don't know, I don't have that information. But it could already change my database, and it could be halfway done. So that's what I know. And then what should I do when I recover it, right? I'm going to scan the log from the end to the beginning. I'm going to say, okay, I'm going to undo all the changes by this transaction T. I'm going to abort it, okay? So the first record I'm going to see is this record. It means that this transaction could potentially already update the B, but here is old value. Then I'm going to replace the on-disk version of B to 8. Maybe it's already 8, right? Maybe this transaction hasn't touched B yet, but I don't care, okay? I'm going to bring B to the old value. And then I go back to the next record, say, so this transaction potentially also touches A before it crashes, right? The old value is 8. I'm going to also bring this value from 16 to 8, right? I'm going to undo the changes of this transaction until I reach the start record. And then say, okay, so this is the beginning, right? So if I want to abort T, that's all I need to do, okay? And what is the system crashes here, right? So here, right, if you look at this really from if you magically know what transaction to do, right, here essentially, the transaction is almost done, right? It's already reflected all the changes to the hard drive. but unfortunately the system crashes. And then when you reopen the system, what would you do? Well, the same thing, right? So essentially, you are going to say, I'm going to abort this transaction because I have no idea whether it's finished or not, right? So I'm going to look back on my log from the tail to the head. I'm going to undo B, undo A using the old value and then abort T, okay? So what if the system crashes here? So this is a point that you already say, okay, I am almost done. Okay, all the changes are there. The changes are already reflected. I put a commit record in my log file, but just before I try to flush my log, your system crashes. In this case, when you reopen your system, what do you have? Everything in the log is gone. Essentially in my log file, right? I only have this 3 record because that you already flash it, right? So these 3 are on hard drive when we restart the system. The last record, the commit T, is not there because it's only in memory. I haven't flashed it yet, okay? I just about to flash it, but system crashes. In this case, if you open it, you only see the 3 record. You are going to do the same thing, okay? You are going to undo this transaction, even though it's almost done, but you have no idea whether that's the case or not, right? So you are going to undo the value of A, undo the value of B, undo the value of A, and abort T. What if the system crashes here? In this case, right? So when you restart the system, you see 4 log records. And you know, okay, all the changes from this transaction is already there, being reflected. I have a commit record in my log file. Maybe I hadn't tell the user the transaction committed yet. Maybe I crashed in the middle, right? And then I can tell the user, okay, so this is a committed transaction. All the changes that you wanted to be done before my system crashed is actually already there, okay? But unfortunately, my system crashed in the middle, but now I reopen it, all the changes you want is there. Don't worry, your transaction committed, okay? So this is actually what's going to happen. So as you can see, right, because you want to recover from failure, right? So we have multiple very important design points. That is, before you allow the transaction to do any real change to your database on your hard drive, bring the information from in-memory to hard drive, I want to make sure all the old values are on my hard drive to make sure if the system breaks in the middle, I can always recover all my potential changes to hard drive. Okay, so this is one crucial design part. And second, I really want this commit record to be flashed to the hard drive after my database have done all the changes it wants to do. Okay, so this is actually another design point. Okay, given this, no matter where the system crashes, you have a way to recover it or to undo it. Okay, so any questions up to this point? There's some in the chat window. One question, what if it crashes during flash and we lose the log? Yeah, so that's okay. So here we are assuming the flash operation is atomic, right? So that is whenever I flash, like nothing can happen in the middle, right? So if something happens in the middle, right? So that's a little bit more complex, right? But the high level idea is when you build a system, you try to build the atomic flash. Okay, and then there's a whole bunch of things you can do that. Given that, right? So you can actually do whatever we are talking about in the course. Okay, makes sense? And someone raise hand, right? Go ahead.
Yeah. Does every file have their own log? So sorry, every transaction have their own log, because if they share one log file, how would they coordinate the accesses?
Yeah, very good question. depends, right? So that's really an implementation issue, right? So also depends on your design goal, like how many transactions you try to support, right? I mean, that is kind of depending on which database you are using. I actually don't know what PostgreSQL is doing. Yeah, but you are right. When you have multiple transactions sharing the same log, there's some special consideration that you need to do. Yeah, so it's actually not that easy. I actually don't know. I don't know what PostgreSQL is doing. Yeah. But
Okay.
I would think they have a share log. Yeah, so I would guess they have a share log. Yeah.
Okay, thanks.
Okay. Okay, great. So what's the problem of undo logging, right? So if you think about this, there are multiple things. So first one, when you think about recoverability, right, we should always think about, and not always, but often we think about the performance, right? Because in the worst case, you can always keep dumping the database to hard drive, right? So you have a naive solution. We want to think about performance. And when we think about performance in this course, we think about the number of I/O, right? Number of data amount of data movement. So let's think about how much data movement I need before I can commit a transaction if you are doing undo logging. Before we commit, what do we need to do? We need to flush the log. Sorry. Yeah, so we need to flush two things. We need to flush all the changes to database, right? So because only after that, I can write the commit record to my log. And only after that, I can commit, right? I need to flush out all my changes to database. I also need to flush out all my logs, right? Before, because before I can do anything to my database, I need to flush the log, right? So, and as you can see, the log is almost as large as all the changes I want to make, right? So this is actually going to double the amount of I/O that I need before I can commit a transaction, right? And clearly that's not something that I want, right? I mean, it's a baseline solution, but potentially I could do better, right? I don't want to double it. So how can we do better? To answer that question, right? So let's look at one alternative login strategy, okay? So instead of relying on undo of uncommitted transactions, what if I rely on redo, right? Whenever I put things in my log, what if I do not put the old value? I put a new value. I put a new value into my database. If transaction T modify database element X, I put transaction T want to bring the value of X to this new value. And before I modify anything on my hard drive, I flash my log together with all the new values and the commit record to my hard drive. What if I do that? And then if the transaction crashes in the middle, I redo it, right? So what if I do that? So that gives us a redo login, which is actually very interesting. So let's follow this step by step. Again, so like we have these transactions deal with two objects, A and B, right? So, and then if you look at the log, I have my start record here, right? At the beginning of the transaction. Whenever you want to write something, right? I put a log record here. I say, okay, transaction T, bring A to 16. Okay. And then if you want to write B, I say, okay, transaction T, want to bring B to 16. And they'll say, okay, I'm done. And then I will put one record in my log, say commit T, T committed. I flush my log, and then allow the transaction to commit. I tell the user, okay, it's done. Yeah. And then in the meantime, in the future, I could potentially output A, output B. Essentially, before I commit to the user, the database hasn't been changed yet. Why? Because all the changes I want to do is already in the log, and I made sure they already flush to the hard drive. Okay, so I don't need to really reflect the real thing before I can tell the user it's committed. So what if we do this? This is redo logging. As you can see, it's actually 2 times cheaper than undo login if you only measure IO, right? So what if the system crashes and we want to do recovery? What would be our strategy, right? Yeah, I'm going to look at the log. If I have a commit T record is not in the log, it means that I haven't flashed my log yet, right? It means that transaction T hadn't made any changes to my hard drive, right? Because all the changes can only happen after commit T record, right, in our protocol. So then I just, then I do nothing, right? I bought the T, whatever, right? T hadn't done anything yet, right? If there's a commit record in my log, the caveat is that it doesn't mean all of its changes are already on my hard drive, because all the logs are there, but maybe I haven't applied all of its changes. Here's what should I do? I already told the user is committed, right? I need to redo the changes of T. Okay, what should I do? I need to scan the log from the head to the tail, the other way around, because I need to redo it, okay? I'm going to scan the log from the beginning to the end. And whenever I see a new record, TXV, right, I kind of update the X to the new value. Okay, I kind of redo the changes that transaction T want to do. Okay, and for each incomplete transaction, I just abort them. Okay, so this is my strategy. So let's look at some examples, right? Assuming the system crashes here, and then you reopen your system, what would you do? So here, right, so it's after I flush out the commit record. If you do this, if the system crashes here, right, you are going to see, okay, so I have a commit record. I know in my log, I have all the potential changes this transaction want to do in my database. And I already told the user it's committed, potentially. And what should I do? But I'm not sure this transaction changes how be reflected. There's no way I can know about that, right? I'm going to start from the beginning of the log. I'm going to change A to 16, which in this case, yeah, A is already 16, I'm happy. I also want to change B to 16. B is 8, I change that to 16, right? Essentially, I have redone all the changes that T want to do on my hard drive, okay? What if your system crashes here? That is, your transaction finished. I already put the commit record in my log file, but unfortunately, just before I flush it out, system crashes. Okay? So in this case, when you reopen the system, what would you see? And you see an empty log file, right? In this case, you are sure that nothing has been done by this transaction to my hard drive, right? Because I can only do changes after you flush your log, right? So then what do? T doesn't exist. There's no effect from T, right? So I do nothing, right? And similarly, what if the system crash here? I do nothing, I do nothing, I do nothing, right? So as you can see, it's actually much more efficient compared with undo login, right? Before I can tell the user that I committed, right? I only need to flush the log, but not the actual changes, right? So that's almost 2 times saving, right? But what's the problem? What's the problem of redo login? Well, there are actually multiple of those. The first one is, let's think about how long the log need to be. In redo login, the log could be very, very long, right? Because even though I commit a transaction, I have no idea whether all of its changes are reflected on my hard drive or not. So I need to keep the whole log. I need to keep the log until the beginning of my database. Because all those transactions, I have no idea. Maybe their changes are in my disk, maybe their changes are not. I need to keep all of those. Potentially, if you do really naive redo login, right, your log file could be very, very long. So, and also when you recover from it, you need to start from the very, very beginning of the log, right, to really redo all the transactions, because even though there's a commit record in my log, doesn't mean all the changes of transaction are already reflected on my hard drive. Of course, there are potential solutions, right? If you go to the textbook, there's something called checkpointing, right? It's a very natural idea, right? Periodically, I say, okay, everyone flush out your changes, and then I can start a new log, right? If you allow me to do that, right? So I can actually periodically shrink my log, right? So that's something that you could do. And of course, if you go to real system, it's more complex, and textbook give you some idea about how to do that. If you put this side by side, right? Let's compare undo and redo. The high-level idea of undo logging is that your data written to disk before the commit record is flushed to log. Okay, potentially you need more I/O before commit, because I also need to flush the log and to flush the actual changes. On the other hand, for undo logging, right, all the modified data are in buffer, right? So until commit, right? So potentially you need a much larger buffer, right? Because I have more changes like in memory, right? Because I don't force you to flush out all those in-memory changes when you commit, right? So potentially I need a larger buffer, right? So that's actually the trade-off, right? So, and also there's some small thing about redo logging, which get a little bit more complex, right? So here we are actually taking a really simplistic view of this, right? We are actually assuming what? We're actually assuming whenever your database outputs something, like flush some object out, you can really flush out essentially like a single tuple, right? And we all know that's not the case. Whenever you flush things out, like both for the page, so like both for log and also for the actual changes, you are flashing out a whole page, right? If you look at redo logging, right? So the basic assumption of redo logging is a transaction cannot make actual changes to my hard drive before you flush out the commit record in the log, right? And that's our basic assumption, right? You need to flush out the log, and then I start to do my actual changes. But what if you have two transactions? One make a change on object A, another make a change on object B. And unfortunately, both are on the same page, right? Whenever I flush something out, I'm always going to flush out a single page. And then when T1 commit, right, we cannot flush out P, right? Because otherwise, both of the changes A and B will be reflected on my hard drive because they're on the same page, but T2 hasn't committed yet. I hadn't flushed out the log of T2, so I cannot make any changes on T2, right? So you are forced to keep all the changes done by T1 in buffer, even though T1 is long gone, it's committed long time ago, but you cannot flush it out because T2 hasn't committed yet. When you have many transactions making concurrent changes, at the end of the day, you are putting really a lot of pressure on your buffer manager, right? Because this is a hard constraint. I cannot evict that page, right? So at the end of the day, if you have a very small buffer, maybe you cannot evict any of the pages, because whenever I evict them, it means that I need to reflect the changes, but I cannot because of my redo logging protocol, right? So that is kind of a potential problem also for redo logging. So how can we handle this? How can we navigate the trade-off between undo logging and redo logging? And also how can we fix this problem? So there's something called undo redo logging, which is a very interesting way of naming it. So the idea is actually very simple. Undo logging and redo logging have their own pros and cons. How about we combine them, have a hybrid approach, right? Whenever it's more beneficial to undo, I undo it. Whenever it's more beneficial to redo it, I redo it, right? All I need is enough amount of information for me to do both. So the high-level idea is as follows. Before you modify any database element on disk, you write to the log in memory a record that contains both the old value and the new value. Transaction T want to update X. The old value is this. The new value is this. You write this to your log file. To your in-memory log, and then you flash your log before actual changes are made on disk. Okay, this is your protocol. So this is one example, right? So essentially, you have your in-memory log. Whenever you want to update A, you write the old value is 8, new value is 16. For B, the old value is 8, the new value is 16. Before I do any changes, I flash my log. I just flash it out. And then I just label the whole, I just put another record commit into my system, and I'm done. Okay. So assuming you are doing this strategy, and assume the system fail at different points, right? So sometimes, right? So for example, like if you see essentially like the commit record, right? Like when you really kind of recover it, right? So you know it's kind of it's a committed transaction, right? So and then I need to redo it, right? And whenever you see commit's not here, right? So I kind of need to kind of undo it, right? Like you have the old value, whenever you need to redo it, right? So you actually have the new value, right? So you can make this little bit kind of not better, but have different behavior if you force the system to flash the log immediately after you have commit. Okay, so this will have different behavior, but there's one paragraph in the textbook that specifically discuss whether you should flash the log immediately after you have the commit record in your log in memory. Okay. So when we go back home, right? So like we go really detailed into undo login and redo login. The high level idea of undo redo login is very similar, right? So there's kind of one section in the textbook go real detail like into this, okay? And including these two alternatives, right? Whether you have commit record or whether you have commit record, whether you flash log or not, right? So what is the different behavior you are going to have in your database? When you go back home, read that section. It's going to be very boring if you go through this again in lecture because it's very similar to what we had before. Go back home, read that, okay? And I think it's very similar to undo read login as you can see. Okay. So this is actually about these 4 properties, right? So last week we talked about isolation and consistency. Today we talk about atomicity and durability. So if you think about where we are, right? So for a single machine, when you have multiple transactions, yeah, we kind of have a high level idea about how to deal with that. So now let's think about a more complex case. What if you have multiple machines? And actually, what if you have multiple databases, right? So when could that happen? So thinking about you are building the next generation of Priceline, okay? That's actually something that you can book your vacation, right? So you look at their website, there's actually something called, you can actually search hotel, flight, and car, right? I mean, you can also book them individually, right? So essentially they are going to talk to a hotel database, they're going to talk to a flight database, going to talk to a car database, but you can actually book everything in a single transaction, right? So if you are thinking about you are building this, what is the thing you are trying to do? Essentially, you have your future Priceline. I have no idea whether they're building this way, by the way, just something like this. You have a hotel database. Some database deal with hotels, right? And some database deal with flight, and some database deal with car. And users say, okay, I want to book a bundle of these 3. So the transaction that you are trying to run is going to say, okay, I first book a hotel, I book a flight, and then I book a car. And you are going to send different transactions to each of these databases, right? For hotel database, give me this hotel, flight, give me this flight, so on and so forth. So assuming this is our mentality model about distributed transaction, there are so many different, you can define it. Assuming this is the thing we want, okay? I have a large transaction coming in to the coordinator, which is going to translate that into a whole bunch of smaller transactions to each individual database or each individual machine. What are the challenges here? The challenge here is that getting this right is actually very hard. And in this course, there's no way we can talk about the whole thing, right? And also getting this right in the meantime also make it fast even harder. As a general rule, when you see Jim Gray and Leslie Lamport write a paper together, that's something hard to do, right? But we are going to scratch the surface to talk about the high-level intuition about this. The high-level challenge is that if you have single node atomicity, that is on a single database, hotel, flight, and car, I make sure I give you atomicity and durability. It doesn't automatically imply distributed atomicity of the large transaction. So that's very simple, right? So assuming the car database fail, right? So even though for each of the database you have atomicity, you actually do not have atomicity for the large transaction, right? Because your change didn't get reflected in the car database, it's reflected in the hotel, in the flight database, right? In terms of the large transaction that I need to book a bundle of this, it's not atomic. You only run part of this, right? So that is a fundamental challenge. You have different players in the system. For each one of them, they can try their best to give you atomicity, but that itself is not enough to enforce the distributed atomicity of the large transaction that I want to do. So we need to design a protocol also for this, right? And we talk about how to use login, all the type of things to have atomicity for a single node. Now I have multiple machines, I have this coordinator. What should I do? So that actually gives you something called a distributed commit. It's actually a very large research area that even today is actually very active. So one thing that you can do is called two-phase commit, which actually try to say, whenever you want to commit something, here's my protocol. I kind of decompose it into two different phases. The first phase, my coordinator here is actually my kind of price line service, right? Who receive this large transaction going to say, okay, everyone just vote. Tell me whether you are willing to commit this transaction or not. Okay. And each node is going to say, okay, no, okay, let me look at it, whether I'm able to commit. And then if everyone say yes, the coordinator is going to ask all the nodes to commit. That's the decision phase. Okay, so it's collect the vote from everyone and look at them. Oh, everyone says yes. Okay, let's commit. So this is something called two-phase commit. Okay, in these two different phases, collect information and then make a decision. That seems very simple, right? But to get it right is actually not that easy. The problem is that the coordinator and the worker can fail at any time. And also when you fail, for example, when the hotel database fail, the flight database doesn't know about it, right? So you need to have a very carefully designed protocol to make sure when the failure gets into the way, right? So you still have this, I mean, you still want to have the protocol to work, right? And because the coordinator and worker can fail at almost any time without all other workers knowing about it, the whole thing actually become a little bit tricky to understand, right? And also, how can you make that faster, right? How can you have a better voting strategy, better decision strategy, right? So that is something that we are going to talk about on Friday when we talk about how to build a distributed database. We are going to start from distributed commit, and then we are going to talk a little bit about distributed query processing. And also, if you have time, we are also going to talk about key value stores. Okay, so that's all we have for today. And if you have any questions, just speak up. I'll be here. Otherwise, I'll see you guys on Friday. Yeah, if you have any question, just speak up. Okay, so if there's no question, see you on Friday.